In this video, we will be discussing helium, an element discovered on the Sun. The discovery of helium began in 1868 with two scientists independently observing the spectroscopy of the Sun during a solar eclipse. The first of these two scientists was Pierre Janssen, a French physicist and mathematician who studied at the University of Paris and also had an interest in astronomy. On August 18, 1868, during a solar eclipse, Janssen observed the spectral lines of the Sun's chromosphere, which is part of its atmosphere, and noticed a bright yellow spectral line of wavelength 587 nanometers. Janssen noticed this line to be very slightly different from a yellow spectral line of sodium, as you can see in the diagram below, and thus distinct from the spectroscopy of any known element at the time. For this reason, he is in part credited with the initial discovery of helium, along with another scientist known as Joseph Lockyer. Sir Joseph Lockyer was a British astronomer who had a particular interest in the Sun. Lockyer, independent of Janssen, also observed the Sun's spectroscopy during the same 1868 eclipse and noticed the same yellow spectral line as Janssen did. Lockyer named this unknown element helium after Helios, the Greek god of the sun. And because of this uncanny coincidence in that both Janssen and Lockyer independently discovered the same thing at roughly the same time, both scientists impartially share credit for the discovery of helium. Due to the contributions of Janssen and Lockyer, helium was the first element to be initially discovered outside of Earth. In fact, it wasn't until 1882, 14 years after Janssen and Lockyer first noticed it on the Sun, that helium was found on Earth by Luigi Palmieri. Palmieri was an Italian physicist who was appointed as the director of the Vesuvius Observatory in 1854. And through this work, upon examining samples of lava from Mount Vesuvius, Palmieri noticed the same characteristic bright yellow spectral line observed by Janssen and Lockyer over a decade prior. This discovery was significant as it was the first indication of helium's existence on Earth, as before it had only been observed in the Sun's chromosphere. Nonetheless, helium wasn't actually isolated until 1888 by American chemist William Francis Hillebrand. Prior to studying geochemistry, Hillebrand studied at Cornell University and received his PhD in inorganic chemistry from the University of Heidelberg in 1875. Through studying samples of uraninite, a mineral largely consisting of uranium dioxide, Hillebrand noticed that a gas was produced. And while this gas was in fact helium, Hillebrand mistook it for nitrogen after spectroscopic analysis. Nevertheless, it marked the first time that helium gas had been isolated on Earth. It wasn't until 1895 that Scottish chemist William Ramsay used similar techniques as Hillebrand to isolate and correctly identify helium gas, confirming it with Lockyer's spectroscopic observations almost 3 decades earlier. Although Hillebrand is not often credited for his methods, his work ultimately paved the way for the eventual confirmation of helium as a new element.
Spectroscopy uses the fact that atoms of each element emit light of a specific wavelength. When energy is given to that atom specifically, it emits light. And that can be broken down, that light that is emitted can be broken down into specific wavelengths. And wavelength is correlated with color, so each wavelength, the wavelength is separated by a diffraction grating, which we'll talk about later. And each of those wavelengths is correlated with a specific color. So the diffraction grating separates the light into constituent wavelengths, and these constituent wavelengths are specific and unique to each atom. So spectroscopy serves as a great way to identify the atom. So, for example, in order to figure out atoms in outer space, as they figured out helium on the Sun, they can't identify the atoms using other means. So spectroscopy is an excellent technique for atoms we can't necessarily reach. So modern spectroscopy uses diffraction grating. So in this picture here, you can see the diffraction grating. It's these slits here, and it uses that diffraction grating to separate the wavelengths of the constituent light that has been emitted from the atom. A charged coupled device is then used in order to capture what goes through the diffraction grating. So a charged coupled device, or CCD, is an integrated circuit that uses capacitors to transfer electrical charge, and these are often used in digital imaging and camera technology. So most modern cameras use these. And it's basically a way to capture the different wavelengths and record them, and then they are converted into from a 2D spectra into a 1D spectra, and that's the spectra you're used to seeing. And then today, NMR and IR are powerful uses of spectroscopy. So NMR spectroscopy, or nuclear magnetic resonance spectroscopy, observes local magnetic fields around nuclei, which identifies the atom. So in this picture here, this graph shows different peaks, which basically correspond to the different atomic nuclei that are labeled here. And then diffraction grating. Diffraction grating is basically a series of splits. As previously discussed, the diffraction grating are used to separate incident light into its constituent wavelengths. And they're basically here, you could kind of see this line here is represent the diffraction grating. All these slits are parallel and close together. So this incident light of the atom in question is put through the diffraction grating, which separates it. And this can be done because different wavelengths are diffracted, or basically deflected through the slits at different angles according to their specific grating relationship. So different wavelengths have different angles. Basically, they bounce off the slits. And these different grating relationships basically reflect on the bright light spectra of the specific atoms, since these different wavelengths have hit the spectra in different places accordingly.
So as Ben was talking about before, through atomic emission spectroscopy, we're able to identify the wavelengths at which photons were emitted. These spectrums are kind of like a fingerprint for each atom. None of them are the same, which helps us not only identify single elements, but even compounds and heterogeneous mixtures, if we separate them into its elemental forms. On the slide, we have examples of two spectrums for you guys to look at. On the top spectrum, we have the helium spectrum, and in fact, this is the yellow line that corresponds to that 587.49 nanometer wavelength that prompted Pierre Janssen to find there was an undiscovered element and spectrum. As you can see, there are many more emissions shown on the helium spectrum than on the hydrogen spectrum. We believe this to be the case because helium has more electrons than hydrogen does, and more electrons being excited will give more spectral lines to be observed in different places. So given this, we are able to identify atoms according to their unique bright emission line spectrums. With the ability to analyze line spectra and identify elements, we are able to apply spectroscopy into various fields and for various different purposes and studies. There are a few applications of spectroscopy that are not only used to identify atoms, but also go a step further to aiding in providing evidence for numerous theories being studied. For example, theories on the Big Bang, the expansion of space, and galaxies all use spectroscopy to analyze the credibility of scientists' hypotheses and traces of early elements in the universe. So when celestial bodies such as stars, asteroids, planets, and comets, it would give off radiation and frequencies, which would then be detected by the emission spectrometer. After we have the majority of the spectrum complete, we are able to analyze the spectra and determine where certain celestial bodies are relative to Earth. Over billions of years, scientists have discovered that the celestial bodies display the Doppler effect in terms of observing line spectra. The Doppler effect is basically when objects and stimuli are much more apparent when closer to us than when going further away from us. So imagine a train, and when you hear the noise grow louder as the train approaches, and when you hear the noise fade as the train moves away from you, that's kind of what's happening with space. When celestial bodies come closer to us, Spectrometers pick up much more radiation and frequencies, and therefore more emission lines, than if the celestial bodies were moving away from us. In that case, we'll see a drop in emission lines on the spectrum. With the use of modern spectrometers, scientists are claiming that the universe is expanding rapidly, and it's all due to spectroscopic data. Spectroscopic data can also be used to improve the chemical efficacy of drugs. Since each element has its own emission and absorption spectrum, we are able to identify the elements and components of mixtures. If we can figure out the necessary and advantageous molecules that react well with our body and cure a certain illness, then we can take any mixture or sample, separate it into its components, and identify traces of the elements in the mixture, analyzing the wavelengths at which it is absorbed with. With this, we can alter the chemical composition of certain drugs. Lastly, hospitals and anesthesiologists use spectrometers to analyze respiratory gases and improve them. So each molecule of gas will give off infrared radiation at which they will absorb them at only certain wavelengths. Given certain molecules will only absorb them at certain wavelengths, we can determine the identities of the gases involved and even their concentrations depending on the abundance. So in the top right, we have an example of a spectroscopic reading of sevoflurane, a chemical used in anesthesia. And although we don't have to understand this reading as well as the doctor does, we should know that the higher the peak, the higher the abundance of a certain element in a region of the overall molecule. Obviously, these are very few applications out of thousands of things you can do with spectrometers. So as you can see, spectrometers have many more uses in the real world other than discovering new elements, although they're pretty cool too. So I know we've been talking a lot about spectroscopy and scientific principles throughout our presentation. The truth is that these techniques are the reason we are able to identify and use chemical elements appropriately. If it wasn't for spectroscopy, we wouldn't have discovered helium, and none of the things we use helium nowadays would be possible. So we should not think about helium for just balloons, but also helium because it was discovered. Like for example, we can use it in MRIs and NMRs, which Ben actually talked about early in the presentation. So with the extremely high amount of radiation and frequencies that are given off by the MRIs and NMRs, we need a super cool liquid to recover and reduce the amount of frequency and radiation. Helium does just that. What's actually kind of funny is that helium was discovered through spectroscopy, and now we are using helium in modern spectroscopic machinery. Also, deep-sea diver tanks are filled with about 35% helium, along with oxygen and nitrogen, obviously. The scanners that we see at the stores and checkouts are actually neon helium lasers that scan the barcodes and QR codes. Lastly, helium is used in numerous scientific instruments, most popularly the Large Hadron Collider. This instrument is basically a particle accelerator, where physicists are able to test principles of particle physics by learning about the existence of new particles that could have existed in the early universe, and how the universe started. With this instrument having over 1,000 dipole magnets and bending really high energy particles, helium is actually used as a recovery cooler to drop the machine down to about 4 degrees Kelvin. So overall, we can pinpoint everyday uses of helium in the real world, and the discovery of this element was all thanks to the 4 scientists we discussed in the beginning of the presentation, and the methods of spectroscopy that are used to this day. Thank you. And these are all our sources.